Thank you for the invitation. So this is the talk title. So I will, today's talk will be 3 parts. And the first part will be the sigma k Nierenberg problem. The second part, sigma k Lunarnirenberg problem. And part 3 is about some conformally invariant equations in 2 dimensions. The above 2 parts are about dimension n greater or equal than 3. So first is the Nierenberg problem. So the question is on S2. And so the question is, this is the round sphere. So whether for function k, whether or not this is the Gauss curvature of a metric conformally equivalent to G. So conformally equivalent to G, meaning this is the metric, this is the G, so there's a positive factor. So this question is equivalent to solving a PDE on the sphere. So this is the PDE on the sphere. So, well, the same question can be asked on sphere n greater or equal than 3. And so change Gauss curvature to scalar curvature. So this is still, write the conformal metric this way. And then the PDE is exactly this PDE. So certainly one can ask the same question if we change sphere to some closed compact manifold, but actually on sphere it's more difficult because of the non-compactness of the conformal group of the sphere. So one can see a necessary condition from here. One just integrate the equation. One see that k has to be positive somewhere. You integrate the equation on the sphere. So the Laplacian term will drop out. You will see that. So from now on, I will only look at k positive. So in studying, so there have been a lot of work on this equation, and it's not possible for me to give any kind of like survey or something. So I will just mention one important ingredient in handling such equations on the sphere also. And it's about the blow-up analysis of solutions. So to prove existence, one way to prove is try to understand what happens if there's a sequence of blowing up solutions. So in 2 dimensions, Alice Chang Pao Yang proved there's only 1 point blow up. There cannot be 2. In 3 dimensions, Bariko Hong and Shen Zhang. And so I have some work for n greater or equal than 4 for some flatness of this k at critical points is beta between these 2. So actually more than 1 point blow up can occur on the sphere, and even infinite energy blow up. So the energy become more and more can occur on the sphere for this equation. So this talk will be about some analogous problems. For the first part is about the sigma k Nierenberg problem. So what one does is just to change sigma scalar curvature to sigma k curvature. So what do we mean by sigma k curvature? So on a Riemannian manifold, we have a metric G, then there's a tensor called Charlton tensor, and given by the Ricci and the multiple of scalar curvature. So the trace of this tensor is actually the scalar curvature. This is the scalar curvature. And so if we denote the eigenvalues of this tensor with respect to the metric G by lambda 1, lambda n, so when we take the sum, we get the scalar curvature. So putting it this way, so you can have other kind of curvatures. If you take a kth elementary symmetric function, we call that sigma k curvature. So we can ask analogous questions saying that on the sphere, for what kind of k, one can have a conformal metric so that the sigma k curvature is equal to this function k. For this shortened tensor and associated fully nonlinear equation, there have been quite some work on this subject. So I have no possibility to survey. I think this is starting around 2000s, something like that. Yeah. Okay. So first part is about this sigma k Nierenberg problem. So so the first result on this for sigma k is by Alice Chang, Zhengchao Han, and Pao Yang. And one can, well, the statement is like this. One can only read this statement for k with isolated critical points. So this function k is on Sn. So let's assume that gradient k equal to 0. This is critical point, and such critical points are isolated, and assume that this k satisfies that. Once you can prove the state things for that, the rest actually will. So let's just read that. Yeah. So what is the then what is this number? This number is the index of that. So this is the index as isolated zeros of gradient k, or you can also say this is -1 to the number of negative eigenvalues of the Hessian at that point. So this is the like the Morse index of this case. So if this number is not 0, then they proved that there is a solvability and the compactness under this. So we look at it for spheres in dimension n greater or equal than 3. And let's also not just look at isolated critical points. And this number is the same way. Put some, yeah, this is the number. So you give a function k, and if this number is not 0, then there is a solution. There is a solution. So this is the statement. So in dimension here, if k is between half dimension and n. So we do not know for dimension less than n/2 and greater or equal than 2. So this statement we do not know there. So this is the restriction. So if that index is not 0, then there is a solution. So this number is actually a degree counting for all the solutions. So a crucial ingredient in analyzing this is an analysis of blow up. So suppose, so we try to prove that all solutions to the equation have, so we try to prove that all solutions is bounded. So we want to prove that suppose you have solutions, we want to prove a priori estimate. So the proof can be done by, we do as usual by contradiction argument. Suppose there's a sequence of solution the maximum goes to infinity, we see what happens. So this is the contradiction argument. So the maximum goes to infinity. So in a paper with Luke Gwynn, this is about the compactness of Yamabe problem for k equal to n over 2. And we analyze there can only be one point blow up. There can only be one point blow up. And also this point of blow up carries one energy. And away from the blow up point, so they are comparable strengths. So the minimum will be happening there. And also the minimum can be controlled by the maximum with -1 plus a little bit power. So this kind of control are enough for us to prove compactness for the sigma k Yamabe problem in half dimension. Well, here actually one needs to strengthen that a little bit. So the strengthening is to make this little o to disappear. Yeah, so just strengthening. So this is needed. Yeah. So here, so the way to prove it is to show it like this. Suppose we have a sequence of blow up point where maximum occur. So let's take this to be the pi, like south pole, and minus pi will be there. So this phi, you basically, it's a conformal transformation, you just stretch it somehow. So you pull everything here to there, to the opposite place. So then you stretch it that way. And so let's say you put a small sphere here. Okay, this sphere, let's say this distance, radius is small, it's like UIPI to minus to this power, you stretch it, say, to the equator. So you stretch it this way. So this is your phi. Yeah, you can write it down. So then you make a conformal transformation UI tilde, and to normalize at pi to be 1. So then it will still satisfy the equation with, the equation is satisfied by UI tilde with ki composed with k composed with this phi. So same equation. So then the estimate we want to prove here translated to, for this UI tilde, you wanted to control a uniform bound near the opposite. So this is just reformulation, it's the same thing. So, and this we prove, we give two proofs, which are deduced from one is this. So this one says that if we have an equation, this is about subsolution. So this is subsolution. So for subsolutions, if we have it in Rn minus B1, so for this equation, subsolution, so this AU is, when you write it, it's AU is a second order operator. This is a conformally invariant operator. We write W equal to U to this power. It has this is the Hessian, W. So if you have subsolution, if at infinity, qualitatively, you have this decay rate. Yeah. So then if you are able to improve, give a quantitative improvement to this alpha a little bit. So this is the half rate there. This corresponds to some special solutions, de Launoy solutions rate. So if you beat that, then you gain a quantitative rate. So beating the Illinois solution will give you a quantitative control. So with this, then we provide that estimate. Another way to derive it is to provide a small energy implied boundedness statement. So one can. So what it says is, this is also for subsolutions. So for subsolutions, and so we will only, K, even though our theorems is about K greater or equal than N over 2, we will just describe things for K equal to N over 2. That's the most subtle one, actually. So here, the statement is, if for subsolution, if we have small energy, then there's a L infinity control. So in the semi-linear case, this what you will see is a Moser iteration argument will give you this. So this was proved by Zheng Chao for n equal to 4 and k equal to 2, and using Moser iteration type estimate for that. So we also go with Moser iteration type. So for k less than n over 2, so a stronger version of this result was proved by Gonzalez. So the stronger one is actually on a punctured ball. But of course, for this case, the punctured ball statement for this k equal to n over 2 is no longer true. So I will not describe the other parts of the proof. So I will move on to the second part. So the second part is about the Lunarnirenberg problems and sigma k version. So what is the Lunarnirenberg problem? So the Lunarnirenberg problem, it also has geometric nature. It's about the conformal metric with, so this will be the, if you take conformal metric, G is Euclidean, let's call it G flat. So this equation says the scalar curvature is equal to -1 instead of 1. Okay, so in PDE, that says if you have this equation and the solution goes to infinity on the boundary. So they proved that the solution exists and unique. Solution will be smooth. And also, there's a very specific rate to that. And the model situation is when omega is a ball and the solution, the metric is the Poincare metric. So that's a model picture. Okay, so now again, instead of scalar curvature here, if we consider the sigma k curvature, so then we call it the sigma k Lunarnirenberg problem. So then there's a sigma k, this is a kth elementary symmetric function, and the equation will be this equation. So AU is the second order operator we gave earlier. So when k equal to 1, that goes back to the original equation. So when sigma 1, so that corresponds to Laplacian u equal to u to the n plus 2 over n minus 2. So in that case, so we proved that this is with Gonzalez and Luke Gwyn, Gonzalez. So we proved that there exists a unique viscosity solution to that. So if you look at the solution in the category of viscosity solutions, so there exists a unique solution. And moreover, the solution is Lipschitz and going to the boundary also with this rate. So Alice Chang, Zheng Chaohan, Pao Yang proved that this problem has no radially symmetric C2 solution on any annulus. So if you look at you restrict your solutions to radially symmetric functions and look at smooth solutions, there's no solution. So this is very different from k equal to 1. So k equal to 1, you always have a smooth solution. And a combination of these two results just already say that there's no C2 solution on any annulus, because on it you have a solution, and this solution, when you rotate it, it's still a solution. The equation is rotation invariant. So all rotation are solutions, but there's a uniqueness. So all rotations should be the same. So they become radial solutions. But radial solutions, smooth one do not exist. So therefore, no smooth solutions. So this shows that some phenomena, different phenomena, actually there are just no smooth solution for all the annulus. So we look and we examined more. So we show the following: take any annulus. So we already know that there are no C2 solutions. So then what happens to that Lipschitz solutions? So what does it look like? Well, we know the solution should be radial. So then we see that this solution actually, if you have an annulus like this, so there's a sphere inside, and this radius is square root of A and B. So solutions are smooth away from this blue sphere. And it is Lipschitz certainly, and it is C1 to 1 over K up to the boundary in each two pieces. So we have two pieces. One piece is in a smaller one, yeah. So then this derivative actually jumps there. So it doesn't, it only has one non-smooth place, and it's a hyper surface. And actually, it will be interesting to produce some solutions which have other type of singularities. So singular part are not a hypersurface. So we don't have such examples yet. Okay, so this is the situation to understand some more of this solution, because now there are non-smooth solutions. So we are interested in knowing more about these solutions, what singular sets, in what case, for what domain you have smooth solutions, and for what domain you do not have smooth solutions, things like that, and the singular sets, some properties of singular sets, and so on. So, and we proved, and also Nitro question is also, instead of solutions, if one just look at subsolutions, do we have smooth ones? Yeah, there are. So here is a result. So saying this, so it says that there is no C2 solutions, which is a subsolution. So this is subsolution. So there's no C2 solutions, subsolutions, provided in the conformal metric, there is a smooth minimal immersion. So in that case, there will be no smooth subsolution, even just for sigma 2, just for sigma 2. So well, of course, this doesn't say yet, when do you have such a minimal, smooth minimal immersion? Yeah. Well, so a corollary of this result is that if you look at the annulus, then if you look at the radially symmetric functions, so you know that there's no smooth subsolution, just no smooth subsolution. Not only, so the earlier result of Alice Chang, Zheng Chao Han, and Pao Yang said there's no smooth solution, radial ones. So here it says actually there's no smooth radial subsolutions. Yeah. So this result is based on a lemma which says this. So if you have a smooth subsolution, then when you compute the Laplacian on U on the sphere, there is an inequality. There is an inequality. Yeah. So this is the mean curvature. This is the mean curvature of this sigma with respect to this conformal metric, which is the U 4 over n minus 2 G, this Euclidean. Yeah. And this is the mean curvature of this is the mean curvature just for the Euclidean one. So this is the gradient on the, yeah. So there's an inequality. So once you have this inequality, you can see that if everything is smooth, you just integrate on that. So this term will drop out. This term drop out. So if you say this is the second term, if you say the second term is minimal surface, it just disappear. And this has a sign, and this also has sign. So these have to be 0. And so you will draw conclusion very easily once you have this. Well, of course, here it has not say when can you produce that, and but in the radial case you can. So in here is the result with Luke and Jinggang Xiong. So in preparation, so it gives the following. So for any omega, so if for example you have this omega, you have for example this omega, and so on. So as long as the boundary has more than one connected component, okay, ruling out a ball, okay, we know that on a ball there is a smooth solution. This is the Poincare metric. So the fact is, on any bounded domain connected with smooth boundary, the Lunarnirenberg problem has no C2 solutions. So there are no C2 solutions. So there are many questions remains which are not known. For instance, okay. So if omega, let's take a very good situation, is strictly convex. Okay. So then smooth, boundary smooth, very nice. Bounded. So whether the sigma k Lunarnirenberg problem is smooth. So whether or not this thing is completely determined by, is somewhat determined by the topology of the domain. So it's not, we don't know. So from this end, it would be nice to see whether one has that. Yeah. We don't know this. Yeah. So now I will go to the third part. So the third part is as follows. So we have been looking at conformally invariant equations in dimension greater or equal than 3. And that equations goes hand in hand with this Shelton tensor. So, and there have been a lot of work on that. And naturally, one asks, what happens in dimension 2? So in dimension 2, one can look at equations under Mobius transformations, not only more restrictive than conformal. Yeah. Conformal, in 2 dimensions, you have many conformal. Yeah, you take any analytic function, non-zero derivative, it's conformal. Yeah. So, but in dimension n greater or equal than 3, so a theorem of Liouville says any local conformal transformations will be the restriction of a Mobius transformation. So in 2 dimensions, if one analyze PDEs, which is invariant under conformal transformations, one can write down exactly what they are, just like in dimension n greater or equal than 3. So the statement is this. So you take a Mobius transformation psi and your function. So your Mobius transformation acts on your function u, and this j is the Jacobian. So you have, if you are u, you have u psi. So if you have an h, we say this operator, when you have an h, this means symmetric 2 by 2 matrices, the collection of that. So if this h, this operator has some invariance. Now, what is the invariance? This is for all psi, which is Mobius, and for all u, you have this invariance. You insert u psi into your operator, you will see the psi come out. So if your operator having this property, then these h are completely classified. It has to be given by an f, which is a function on the 2 by 2 symmetric functions, and it is invariant under orthogonal conjugation. Namely, it is f of a matrix is really the a little f of eigenvalue of this matrix. It's the same thing. Yeah. So this h, this operator has to be of this form. This is the conformally invariant operator. So it has to be of this form. And and of course, anything of this form will be conformally invariant. Yeah. So then, like in dimension n greater or equal than 3, so we look at the Liouville properties because, yeah. So let's first look at the Liouville property of that. So here, let's look at in R2. This is R2. So this is where the eigenvalues stay. So here, we call it R1, gamma 1. So this is the place where the trace is positive. This is a half plane. And we look at the cone, which is symmetric. So we look at the cone, which is symmetric. This is the cone gamma. So it is symmetric, meaning when you permute lambda 1, lambda 2, it stays in your cone. So this is a cone where the eigenvalues of the conformal invariant matrix state. So you take a cone, you take any cone, but we rule out the cone gamma equal to gamma 1. You take a cone in between this and gamma 2. So gamma 2 is the positive cone. So gamma 2 is this cone. This is the first quadrant. This is gamma 2. So the gamma is in between. Yeah. So it can be gamma 2. You take any such gamma. So then you look at an equation in R2. So this is the equation. So this is the conformally invariant equation. This is an entire solution in gamma. So this solution has to be of specific form. It has to be this. This is the standard solutions. Yeah. So it has to be this. So it's completely classified. This is the Liouville equation, Liouville theorem for such equations. So once one has Liouville equations, solutions, Liouville theorem, one can expect this type of solutions existence and things like this. There will be results on those. And in fact, we have been examining many of aspects of that and have obtained results like that, analogous to higher dimensions. So this Liouville theorem, an interesting point is this Liouville theorem, we do not need to make any assumption for behavior at infinity. So it's just all solutions. It has to be of this specific form. And certainly anything like that you insert, it is a solution. Yeah. And so what I'm saying is we compare this to a result proved by Yanyan Li and Wenxun Chen, which says that if you have an entire solution in R2, so this entire solution actually corresponds to what we wrote there, is that gamma is gamma 1, and we take that function to be the trace. So then we will see this equation. So for that equation, and their theorem has this assumption, and this assumption cannot be dropped. Okay, this is the volume finiteness for the conformal metric. So this cannot be dropped, and then they prove that all solutions are here. So this cannot be dropped. This cannot be dropped. So the difference here is once you are closing up a little bit, you are becoming a slightly smaller, and you gain some convexity, you gain some positivity of this AU. You gain some positivity of this AU, and that plays important role in the analysis. So this is in the Liouville theorem, and also we have other results also showing the help of this positiveness. Actually, this also when this for the sigma k Yamabe problem, this also it is this positivity, some positivity, the right positivity of this Schouten tensor also play important role there. And there, so the compactness result holds when k is greater or equal to n/2. So that's so here, for k less than n over 2, one still have some positivity there. So the question is how to use it more effectively in higher dimension. And for the sigma k Yamabe problem in dimension, in higher dimension, in n greater or equal than 3, if k less than n over 2, greater or equal than 2, it still remains open. Yeah. So understanding certain things like this should be useful. So, and I will stop the talk, and thank you very much. And thank